Hi, my name is Bailey and I'm one of the co-founders of StakeUp. Today I'll be walking y'all through all the code and the context that is necessary to prepare for StakeUp's audit competition that will be running on Cantina from October 7th through October 21st. The audit scope will be covering both StakeUp's codebase as well as Bloom v2. First off, I'll give an overview of each protocol, and then I'll break down each of the codebases in more detail. StakeUp is a protocol that gives users access to a yield-bearing stable that derives its yield from on-chain tokenized treasuries. The protocol is built on top of Bloom v2 and provides an auto-compounding rebasing stable LST called ST-USDC. This token is pegged one-to-one with USDC and is backed by both idle USDC liquidity and various TBYs. It's an omni-chain system built using Layer 0's OFT and OAP contracts and distributes yield from a single chain liquidity hub that will either be on Base or Arbitrum to all deployments on other blockchains. Yield is calculated using built-in on-chain rate providers that are updated every 24 hours. ST-USDC provides a single token wrapper that allows for composability within DeFi, but the core mechanics of the system really begin with Bloom v2. Bloom v2 is a lending market structured as a modified order book that gives users access to short-dated tokenized treasuries in a manner that is compliant within current government regulation in both the United States and Europe. It does so by matching non-KYC lenders to KYC and compliant borrowers who use lenders' funds to purchase backed finance's BIB01 tracker certificate token. Lenders receive a receipt token called a term-bound yield token, or a TBY for short, that can be redeemed at the end of the token's maturity for their collateral plus any yield accrued during the token's duration. The borrower receives a return based on an interest rate that's set at the creation of the loan. Bloom v2 is pretty simple. It's made up of two contract deployments, the Bloom pool and the TBY contract. The Bloom pool is made up of three parts: pool storage, which represents all global setters and variables within the protocol; the order book, which handles all lender and borrower orders; and finally, the top-level Bloom pool, which contains logic for the final stages of the order flow, which encompasses TBY creation, redemptions, and on-chain rate providers for all TBYs. TBYs are ERC 1155 multi-tokens that represent short-dated receipts for lending into the system. Now, I'll break down each part of the user lifecycle within Bloom v2. A user will deposit USDC into the contract by creating a lend order. Lend orders are aggregated by lender addresses and represent a lender's request for a TBY. Borrowers who are KYC'd then can fill one or multiple lend orders by posting the required collateral amounts for each order. Once that occurs, the open order becomes a matched order. Matched orders represent orders that borrowers have filled and are grouped by lender addresses and subgrouped by borrower addresses. Once market makers swap BAC's BIB01 token into the pool, all orders are converted into live orders. TBYs are minted to the various lenders, and the yield generation process begins. At the end of the yield generating process, market makers will return and swap out the BIB01 token with USDC, stopping yield from accruing for both lenders and borrowers. At this point, the TBYs are eligible to be redeemed by lenders, and borrowers can also redeem their collateral plus any yield accrued. Now, let's walk through the Bloom v2 codebase. So now we're going to walk through the Bloom pool contracts. Everything within the audit is up for grabs within the source directory. You don't really need to look through the helpers or the interfaces, as the helpers are just custom error codes, and then interfaces are just pretty standard interfaces. Within the Bloom pool is made up of three contracts. The Bloom pool, which is then built on top of the order book, which is then built on top of pool storage. Pretty standard. Everything is just pretty simple here. We got two modifiers: KYC borrower, which requires that the caller is a valid KYC borrower, and the same thing for market makers. The constructor pretty much initializes everything, from the TBYs to the tokens that we utilize in the contracts, the scaling factors and decimals, and then it sets the leverage and the spread. the leverage and the spread. The leverage has an upper bound of 100x leverage. In production, we'll probably see that be 50x leverage. And then there's a min spread. The spread is going to be the difference between the TBY rate and the RWA's rate, and essentially establishes the interest rate for the borrower. All the functions here, we just have permission setters from that are gate kept to only the owner. That's whitelisting borrowers and market makers and setting the leverage and the spread. Then the rest here, you just have pretty much basic read functions that hit all of the storage variables. Next is the order book. This is where kind of the meat of the early stage of the protocol's user flow is going to take place in. So anything with like opening lend orders or matching orders, that's all going to take place in this contract. So we see the storage variables. We have open depth and match depth. This is going to be like the total amount of USDC liquidity that is in each one of these stages. So open depth is the total amount of lend orders that exist in USDC. And then match depth is the same thing, but for matched orders. We have a couple mappings here. This first one is all of the users' open orders. So it maps lender addresses to the total amount of open orders for that user. And then we have the user matched orders, which are a mapping of lenders to a matched order struct, and it's going to be an array of these. Looking into this match order struct, it contains the amount of underlying assets that the lender is using as collateral, and the same thing for the borrower's collateral, as well as the address of the borrower. This final mapping is a mapping of borrowers' addresses to the amount of idle capital that they have. This is a concept that we'll get into as we progress through the code base. Now we'll go into each one of the functions of the order book. So the starting process for a lender in the system is to create a lend order. They're going to call this by passing the amount of USDC that they would like to lend. Now for opening an order, what that looks like is just incrementing both the global open depth as well as the open orders for a given lender. Now let's take a look at the fill order and fill orders functions. They are both for KYC borrowers, and this is what creates matched orders. They take in an address or an array of addresses that represent lenders' open orders, as well as an amount which represents the maximum amount of USDC liquidity that a borrower wants to fill the order with. They do identical things, except fill orders iterates through all of these addresses and fills each one, while fill order only fills a single order. Fill order does an address and amount zero check and then begins the fill order process. What that looks like, it gets the order depth for a given user and then calculates what's the maximum amount that can be filled for that user. It then decrements the total open depth, increments the total match depth, and then decrements that user's individual order. After that, we calculate the necessary amount of collateral that the borrower can post by applying the leverage to the amount filled. We get all the matches for that lender, iterate through all of them, and check if a borrower has already matched a lender's order. If they have, then we just increment both the borrower and lend collateral and exit the function. If that's not the case, then we add a match to that array. Once we've filled the order, now it's time for the borrower to deposit. This is a fairly simple process, as we just check if there's any idle capital for the borrower in the system. If there is, then we utilize that idle capital to fill that order, and then find how much remaining amount of underlying assets is needed for the borrower. Once we calculate this, we then transfer that from the borrower's address to the contract. In order to prevent funds from being stuck in the system, we've created functions to allow both lenders and borrowers to cancel their positions. Lenders can cancel both open orders and matched orders. Canceling open orders is simple. Because no borrower has entered the system, lenders will simply just decrement their current order as well as the total open amount, and the assets simply get transferred back to their account. Killing match orders is slightly more complicated, however. As you can see, in order to close a match order, we're going to close them out in a last in, first out manner. We get all of the matches that have occurred in the system, and then we iterate backwards through the array. If a match has no collateral, then we're simply going to remove it. We set a remaining amount equal to the amount that the lender wants to kill, and then one by one we iterate through the loop, taking the minimum amount between the amount remaining and the lender's collateral. If the amount to remove is not equal to the entire collateral amount, then we're going to calculate each of these amounts individually and decrement them from the current match. We don't want to charge lenders for sending borrowers' tokens back to them, so that's what we create the idle capital entry for. Idle capital is only created when lenders cancel their matched order. It essentially allows lenders to be able to use capital that already exists in the system for filling future orders without having to constantly send more tokens to the contract. In the event that lender's collateral is equal to the amount needed to be removed from the contract, we can easily just remove that entry from the array. At the end, we calculate how much has been removed from this entire process and decrement the match depth. After we finish with closing all the matched orders, we get the total amount that's been removed and then transfer that back to the user. Borrowers can also kill matched orders in case they want to receive their liquidity. To do so, they just pass the lender address of the order that they want to kill. We then iterate through each match, find the borrower, and zero out the collateral value. Once this is done, we decrement the total lender amount from the match depth, send this, and then create an open order for the lender. Once this is done, we safely transfer the underlying asset back to the borrower. Like I said earlier, idle capital exists in the system when lenders cancel matched orders. Borrowers can conveniently use this idle capital to fill existing open orders, but in the case they want to receive this liquidity back, they can simply call withdraw idle capital and receive all of the idle capital within their account. The Bloom Pool contract contains all the logic for creating and finalizing TBYs, handling redemptions, and calculating TBY rates. Swap-in creates new TBYs for lenders by having KYC market makers swap in BIP01 tokens for USDC. This kickstarts TBYs for all lenders that are passed within this account's array. As you can see within the handle TBYID private function, there's a 48-hour swap buffer put on all swap-ins from market makers. This means that every 48 hours, a new TBYID is eligible to be minted. Once it's determined what TBYID is being minted, all lender orders that are passed in the parameters are converted from a matched order to a live order. This is very much the same process as the kill match order, except instead of removing the order, we are minting the TBYs to that user's account. After we convert all of the matched orders, we then calculate how much RWA token to swap into the pool using the Chainlink price feed, and then we set the starting price of the TBY. Due to the potential time lag within market maker swaps, the start price is also normalized. Once the start price has been established, we update the collateral amounts and then transfer in the RWA token and transfer out the USDC. Once the TBY is live, we can utilize the getRate function in order to calculate the lender's return for that TBY. The rate encompasses the price from the Chainlink price feed of the RWA asset minus the spread that's taken. Spreads are only taken as long as the rate is greater than 1. At the end of the TBY's duration, the collateral that's backing the token is eligible to be swapped out for USDC. The swap out function enables this to occur, allowing KYC market makers to return the USDC liquidity in exchange for the RWA asset. Within this function, we calculate the percent of the total amount of liquidity that is being swapped out in order to properly calculate the lender return for a given TBY. There's no time limit for the market maker to finalize swaps, as no redemptions can occur until 100% of the RWA collateral for a given TBY has been swapped out. Once a lender return has been established, the borrower return will be established by taking the total amount of assets minus the lender return. These state variables are updated in storage. After the market maker has completed all swaps and the current RWA collateral amount is 0, now the TBY is eligible for redemption. The redeem lender and redeem borrower functions allow lenders and borrowers to redeem their collateral plus any yield that has been generated within the protocol. Lenders' TBYs will be burned and underlying assets returned to them. Due to the fact that no TBYs are minted for borrowers, just borrowers' earnings will be returned to them and all state variables will be decremented. Now that we've gone through the Bloom Pool contracts, now let's take a look at the TBY, our term-bound yield token contract. This contract is fairly simple. It's pretty much just an ERC 1155 token with an only Bloom modifier that only allows the Bloom Pool to call various functions. These functions are the mint function and the burn function. Now that we've seen how the Bloom v2 code works, let's take a look at StakeUp's architecture, which builds on top of Bloom. A high-level architecture overview of StakeUp can be broken down into two pieces, STUSDC and StakeUp staking. While there are many auxiliary contracts within the StakeUp ecosystem, the core features of the protocol can be broken down into these two pieces. STUSDC is an auto-compounding rebasing stable LST that takes in both USDC and TBYs as deposit assets. As the protocol generates yield, there's a 10% performance fee that gets sent to StakeUp staking in the form of STUSDC, where SUP stakers can claim 100% of the fees generated by the protocol. There are 3 tokens within the StakeUp ecosystem that are important to keep in mind during this audit. STUSDC is the main contract in the system, and like I mentioned earlier, is a rebasing stable that is pegged 1-to-1 to the value of USDC. It's built on top of Layer 0's OFT contract, meaning it's natively omni-chain and can be bridged to any supported chain. Wrapped staked USDC is the wrapped version of STUSDC. It is non-rebasing and accrues value as yield is generated. This token is not built on top of the OFT standard, but instead can be bridged to all supported chains using the wrapped staked USDC bridge. Finally, the last token of importance is SUP, or the StakeUp token. Finally, the last token of importance is the StakeUp token, or SUP for short. It's the protocol's revenue-bearing utility token and is also built off of the OFT standard. There will be a total max supply of 1 billion SUP tokens, and stakers of this token are entitled to 100% of the revenue of the protocol. Layer 0 empowers the omni-chain capabilities of STUSDC. All yield and token bridging occurs directly within the smart contracts of STUSDC, allowing the protocol to not rely on external parties besides Layer 0. Now, let's take a more detailed look at the smart contracts within the StakeUp ecosystem. Now it's time to go through the smart contracts within the StakeUp ecosystem. For this audit, all of the source directory is going to be eligible for the audit competition, just like for Bloom pools. There's some things to note as within the helpers we have StakeUp constants and StakeUp errors. These pretty unnecessary to look through for the audit as they're just custom error codes and constants. And then we have a bunch of basic interfaces. The meat of the protocol is going to be within this token section, as well as staking. And then we have some additional other directories, such as rewards, and then messaging. I'll break down each of these directories as we go on. But first off, I'll start with something that's like not as important, and that's the curve gauge distributor. The curve gauge distributor is just for automating curve rewards for one of our liquidity pools. Going through here, it's a contract that's going to initialize the curve pools and deploy curve gauges for those pools. These are just for SUP rewards that will be automated. Within the seed gauge function, this is a permissionless function that will be seeded using a 1 week time intervals, and it will seed rewards based on the calculate drip amount function from the reward math library. The StakeUp reward math library contains a function called calculate drip amount, and this is a generalized function for dripping rewards. It takes place over a 5-year linear period that has linear halving schedules after each year. And it's just pretty much a basic formula that calculates how much tokens to drip out based on the last time it's been called and based on the protocol. The Mint reward library is just pretty much used for calculating Mint rewards. Within STUSDC, there are Mint rewards for users who deposit TBYs, and this library just pretty much states, based off of which chain, how much are the maximum rewards eligible for that chain. Moving on to our token directory, this is going to be the meat of the protocol. STUSDC is the primary contract within the StakeUp ecosystem, as it represents the stable asset that the whole protocol is built around. As you see, we can go a couple layers deep as STUSDC inherits STUSDC Lite, which then inherits rebasing OTF, which then inherits OFT controller, which then inherits controller base, and layer 0's OFT contract. Not going to go over the OFT contract, but I will go back over everything else. So we're going to be renouncing ownership of all these contracts once we deploy, but we still need to have control over the OFT bridges and the layer 0 endpoints so that we can add new chains to the system. We're going to be doing so through these controllers which are pretty much pass-through functions that go to these OFT and OAP setters. The bridge operator is going to be the contract that we use to call these functions. So if we take a look here with the bridge operator, it's essentially just a contract that allows us to set the peers and the delegates and the bridges for all of these different contracts within the StakeUp ecosystem all at once. So you see here, when we set the peers, it does so for all 4 contracts that are layer 0 contracts in the system, and this allows us a simple interface that we can just call and set all of our setters as needed. The rebasing OFT is just a ERC20 token that rebases that also has OFT compatibility. Debit and credit are used for minting and burning tokens during the bridging process. We're not going to utilize them here because we want to utilize them in the STUSDC Lite function, because there's more customized logic that we're going to implement for not only the debit and credit functions, but also the total supply. Everything else in here is just very standard rebasing logic, so nothing that should be specific to the protocol itself. STUSDC Lite is the first Lite contract that we're going to cover here. Within all three tokens of the StakeUp ecosystem, they all have Lite versions. And that means that these contracts, the Lite versions, are contracts that will be deployed on all blockchains except for the home liquidity hub, which, as I mentioned earlier in the video, is on Base or Arbitrum. So these tokens contain pretty much the bare minimum logic that a deployment chain is going to have, and does not have any of the logic necessary for taking in USDC or TBY deposits. So total supply is going to be based on total USD value in the system, because this token rebases 1-to-1 to the value of USDC. So within total USD, all yield in the system is dripped out on a delayed 24-hour basis. The total USD function uses this total USD floor, which is the base USD amount of the contract before taking into account yield. This value is updated every 24 hours as well. So as the yield increases the next day, the total USD floor will also increase. But since we slowly drip out the past 24 hours of rewards every second, we have to update this total USD value to do the same. So we get the yield per share, we take the reward per second and multiply it by the time elapsed, and then apply that to the total USD floor based on the total shares. This is where the total USD floor gets set. Every 24 hours, this function will be called via the set USD per share function, and this can only be called by the StakeUp keeper. The StakeUp keeper is going to be on every chain, and it pretty much handles the yield messaging process from that base liquidity chain to all the other chains. We'll go into detail a little bit more on that once we enter the STUSDC contract. As I mentioned earlier, the debit and the credit internal functions are used for handling the minting and burning of tokens when we bridge them to and from different chains. The STUSDC contract is where the main logic occurs for handling the deposits of USDC and TBYs and all the yield generation process. Going to mention again that this contract, wrap staked USDC and StakeUp token, will all only be deployed on one chain. The rest of the chains will get the Lite instances of the token. Deposit asset is going to be the primary method that we use to mint STUSDC. There is also an additional method of depositing TBYs. When you deposit a TBY, you're eligible for SUP mint rewards. When depositing an asset, we are essentially opening a lend order within the Bloom pool. So, as you can remember from the Bloom pool code walkthrough, we call this lend order function in order to open a lend order. When we deposit TBYs, we cannot deposit TBYs that are already redeemable. So TBYs must still be in their maturity phase, in their duration phase, in order to deposit them. Due to the fact that yields delayed 24 hours in the system and slowly drip down, we have to discount these TBYs in order to not overvalue them. This calculation won't be 100% exact due to the fact that TBYs accrue yield in a nonlinear fashion. As I said earlier, TBY deposits are eligible for mint rewards. Here we calculate the amount of SUP mint rewards are eligible for a given TBY. There's an inverse relationship between the amount of time that a TBY has been minted and the amount of rewards that a user can earn. This is in order to prevent people from gaming the reward system and depositing TBYs close to the end of maturity and then being able to withdraw a maximum amount of rewards without significantly contributing to the protocol's TVL. The redeem STUSDC function allows users to burn their STUSDC and regain their USDC liquidity. If there isn't enough USDC liquidity in the contract, which is possible in the event that all liquidity is within the balloon contracts, we will try to cancel enough orders by killing a lend order or killing a match order in order to regain the needed liquidity that we are trying to withdraw. If we are able to withdraw enough liquidity to redeem our STUSDC, then we will burn shares of STUSDC, adjust the floor of the protocol, and then transfer assets to the user. The poke function is where we get our auto-compounding properties of the protocol from. It is a permissionless function and any person can call it. When a user calls it, if they successfully keep the protocol up to date, they will be distributed poke rewards in the form of SUP. This gets calculated based off of the calculate drip amount function from the StakeUp reward math library. The poke function does a couple things. One, it can only be called every 24 hours, and once that happens, it auto-lends all idle USDC liquidity into the balloon pool so that it can be auto-compounded. After that, it calculates the total protocol value of the protocol in USDC as well as with the TBYs that exist in the pool. After we get the protocol value, we're going to calculate what the USD per share value is. If it is greater than the last USDC per share value and it's greater than the highest USD per share value, we then need to calculate the fee that we're going to send to the system. We must update the user value and decrement the fee out of the protocol value in order to get the new USD per share value, since the protocol fee will be sent in the following 24 hours, not now, so that we can accurately calculate the yield to send to all the different chains. As I mentioned earlier, this is where the set USD per share value comes into play, as well as the StakeUp keeper. So once we need to update the USD per share to reflect the new value, we set the new share on this chain's instance, and then if we have a peer length greater than 0, which means that we have more than one cross-chain deployment, then we will call the sync function on the StakeUp keeper. This sync function sends the new USD per share value and the current timestamp that the yield update occurred in to all chains that STUSDC lives on. This is done through a batch send by sending layer 0 messages cross-chain. After this whole process is done, if there is a previous fee that has existed in the system during the previous poke, we will now send that fee to StakeUp staking. After a yield has successfully been synced in the current contract instance and all cross-chain instances, we will harvest matured TBYs and distribute poke rewards. Going back to the StakeUp keeper, it should be noted that it inherits this LZ ordered messenger. This is a contract that enforces ordered messaging of layer 0 messages. This is in order to prevent messages from getting out of order in the event of delays and keeping the rates and yield accurate. Now that we've gone over ST-USDC, the rest of the protocol is pretty self-explanatory and easy to get through. Wrapped StakeUSDC is just the wrapped version, wrapped non-rebasing version of ST-USDC. In the full instance, we can deposit assets and TBYs directly into the contract, and we can also redeem through the contract. So a user never has to hold the rebasing asset. Additionally, the wrapped StakeUSDC Lite version that will be on all chains has just simple wrap and unwrap functions, as well as share calculations. The StakeUp token is a simple OFT contract from layer 0 that inherits the OFT controller. And on the full instance has a couple functionalities that I'll discuss now. SUP has authorized mentors. This will be either ST-USDC or the curve gauge distributor. This will allow ment rewards to be mented to users, as you can see with this function. There's a global supply variable that tracks the global supply of all SUP on all chains. As you can see, whenever we mint a new token, we update this global supply in order to make sure that we don't go above the max supply of 1 billion. A key feature that we'll get into in a second is the vesting feature of StakeUp Staking. StakeUp Staking natively has a vesting contract built in, so users that are eligible for vested SUP can have their allocation staked within StakeUp, still earning yield on their holdings. Here is the function that the owner can call to mint SUP and start a vest for a given user. StakeUp Staking is the staking contract that allows users who stake their SUP to earn all the protocol fees generated. It is made up of SUP vesting, which is a vesting contract that I mentioned earlier that allows users to earn ST-USDC rewards while still being under vesting schedules. The vest tokens function kickstarts the vesting period for a user. Claim available tokens allows users to withdraw all tokens that have fully vested. And available tokens allows users to see how much tokens that are eligible for withdrawing. The process fees function is called by ST-USDC every time that fees are sent to the protocol. And this function, like all write functions within StakeUp Staking, update the reward index to allow users to accrue rewards. The functionality of the contract is pretty simple. When you stake your tokens, there is a 24-hour time lock that is placed on your deposit where you cannot unstake your SUP until that time lock has passed. The unstake function allows you to not only unstake your SUP, but also harvest rewards within the same call. The harvest function allows you to harvest rewards without withdrawing your stake. Due to ST-USDC's cross-chain accounting, it is difficult to implement OFT within wrapped staked USDC. In order to get around this, we created a bridge specifically for wrapped staked USDC that uses Layer 0's OAP. The bridge operator can set new bridges for each instance, and users can simply call the bridge wrapped staked USDC function to bridge USDC to and from different chains. This essentially happens by sending wrap staked USDC to the contract, unwrapping it, then bridging STUSDC to the destination contract, and then wrapping it again, delivering it to the user. Thank you so much for your time, and I appreciate you helping make our protocol and users' funds safe. For more questions on the audit, competition, and code base, please reach out to me on Twitter at 0xspraggins. I will also be hosting office hours every day, Monday through Friday, at 6 p.m. UTC during the duration of the competition. Thank you.